All right, so we are in our last unit of study for the semester. And that unit of study focuses on gases and gas properties and some calculations related to those things. So one of the things that we have to establish and kind of set up as far as gases are concerned are we need to have a good basis for why we can describe gases the way that we do and the way that the properties of those gases interact with each other to give us things that we can actually measure. And so the overarching theory here is something called the kinetic molecular theory. Now, the kinetic molecular theory focuses on a couple of really big ideas. And we'll get to those ideas in a second. But what's really important for us to understand about the kinetic molecular theory is that it's a model and it is correct most of the time. Now, what we'll find is that there are going to be conditions where the kinetic molecular theory does not work particularly well. And for the most part, we are going to avoid those conditions wherever possible. So we're going to focus on what we would call ideal gas behavior. That is gas behavior that is predictable and directly related to this theory. So wanted to kind of focus on that, point that out before we got too deep into this, because it is important to understand and know that our central theory here does have some holes in it, but we're going to mainly focus on the places where it's good. What does it say? First idea of kinetic molecular theory is that we have gas particles that are in constant motion. Now, this should vibe pretty close to what we understand already about other substances that aren't gases. We know that liquids, those molecules are in constant motion as well. We know that solid molecules are in constant motion as well. They're just moving to a much lesser extent. Gases fill up their entire containers and are in constant random motion as they go. They are always moving in straight lines and basically stay in a straight momentum until they encounter something. Whether they encounter the wall and bounce off of it, or if they encounter another gas molecule and bounce off of that gas molecule. They are always in constant motion. That motion is always straight line motion until it runs into something. As you can see from the diagram here, gas molecules are far apart from each other. So far apart that we generally think about gas particles as having really no interactions with each other. Gas particles are kind of loners in that sense. They don't interact with other things. They're kind of far apart from everybody else, but they are constantly moving. When they do collide with each other, we want to think about those collisions like you would if you were playing pool. The collisions are hard, and they usually result in things getting separated from each other. In the physics world, they would call that an elastic collision. again, what I want you to think about is, let's say you're on one end of the pool table and you've got a friend on the other end of the pool table and you're just throwing the balls at each other. When those balls collide with the wall, they bounce off. When those balls collide with each other, they bounce off. And that's what happens when the gas molecules collide with each other or collide with the walls of their container. They'll hit, but then they'll bounce back off again. There is a lot of space between the gas molecules and each other. So much so that we can kind of consider the overall volume of the gas molecules to be pretty much non-existent. And why is that important? Because that means that when we're describing the gas in terms of how much space it takes up, we can just look at the size of the container it's in and use that as our guideline. So if I have a 2-liter bottle and all of the liquid has been pulled out of it, I can safely assume that I have 2 liters of gas in that bottle. I don't have to worry about, well, how much space is the gas molecule taking up? Doesn't matter. Relative to the size of the bottle, the little particles of gas, because they're so far apart from each other, they practically take up no space. So when I describe the volume of a sample of gas, I'm usually just describing the volume of the container that that gas sample is in. The last piece of the kinetic molecular theory has to do with the molecules themselves. When the temperature of my gas goes up, the speed at which those molecules are moving goes up as well. And again, that should make some sense to us. We know that when the temperature of anything increases, the energy of that something increases as well. And if it's not increasing in terms of potential energy, it has to increase in terms of kinetic energy, which would be the energy of motion. So the higher the temperature is, the higher the energy of motion goes, the faster everything's moving. Because of kinetic molecular theory, we can use those kind of guiding principles to explain some of the most common properties of gases. So for example, we know that gases are compressible. If I have a balloon and I blow it up, I can push on the balloon and squeeze it and make it take up less space. I can take a syringe full of air, I can push on the plunger of that syringe and get the gas to compress down to a smaller size. Or even more commonly, I can take a gas sample and force it into a gas tank and get the tank to exhibit pressures greater than 1 atmosphere. And not have really any kinds of issues with that, because all that's happening is that that large space that exists between the molecules just gets smaller. We know that gases assume the shape and volume of their container. Well, again, that comes down to the molecular theory as well. Lots of space between the gas molecules, so the gas is just going to naturally expand to whatever container it's put into. And we know that gases have lower densities relative to liquids and solids. Again, that makes sense, right? If all of my compact space or mass is now spread out over a gigantic space. My mass hasn't changed, but my volume has considerably. And we see that with gases. We don't see that with liquids and solids. Liquids and solids stay condensed, stay compacted. Their volumes, their densities, they tend to be very close to each other. Gases are way off the chart in terms of small. So with kinetic molecular theory in mind, we can start to look at some of the ways that we measure gases and trying to make some sense of it. Now, for gases, we tend to measure three things commonly. We tend to measure the temperature of a gas, easy to do, we just use the thermometer. We tend to use the volume of the gas, also easy to do. All we need to do is measure the container in terms of its volume. And we can measure the pressure using something like a pressure gauge or a barometer or some other kind of similar tool. But while volume and temperature are things that we have talked about, we haven't really talked a whole lot about pressure. So before we get into more detail about pressure and gas pressure, let's talk about what pressure is in the first place. In physical terms, pressure is the amount of force applied over a given area of a surface. So anytime we exert any kind of force onto an object, we're exhibiting some kind of pressure on that object. Now, whether that pressure is productive in terms of giving us any kind of work, that's a completely different argument altogether. I can push as much as I want on this desk. It's not going to be very easy for me to move it. It's pretty heavy, and I'm not entirely sure it's not going to ground. But the force applied over a given area is the pressure. Now, what does this have to do with gases? Well, in gases, that pressure can be exerted when those gas molecules collide with things. In particular, when they collide with the walls of their container. So the more collisions that happen, the more pressure is going to be exerted. And so when we start getting into measuring the pressure of a gas and comparing the pressure of one gas versus another, what we really need to think about are those collisions. The more collisions between the gas and the walls of its container, the higher the pressure is going to be. So in a comparison kind of way, what gives us more collisions or fewer collisions would be how we would compare one gas to another. And there are a lot of ways that we can go about doing that. In terms of pressure units, the most common unit of pressure is the atmosphere. Atmosphere is abbreviated as ATM. And the reason why this is the most common is this one's kind of the most easy to standardize. This is simply the atmospheric pressure at sea level. So if we go down to sea level, so like right now we are maybe 200 feet above sea level, like that. But if we go down to sea level and measure the atmospheric pressure there, we would get 1 atmosphere as that unit of pressure. Now, the SI unit, that is the International System Unit, which is based on those base units, is the Pascal. Pascal is PA. I'm not exactly sure what happened to my slide here, but it should say 1 Pascal is equal to 1 Newton per square meter. Now, the problematic nature of the Pascal is twofold. First of all, a Newton is not a terribly large amount of force. The second thing is that the square meter is an incredibly large area to measure. As a result, a Pascal is not a terribly large unit of measure. Just as a comparison, that 1 atmosphere, so the pressure of the atmosphere at sea level is equal to 101,325 pascals. And atmospheric pressure is pressure that we don't even think about, because it's constantly being exerted on us at all times. You've got roughly 1 atmosphere of pressure pushing down on your shoulders right now, just from the gases in the air colliding with you. So if the Pascal is kind of an unusable unit, at least in our circumstances where we're dealing with, normal atmospheric kinds of conditions, what are some other common units that we might use? And for that, we would look at something like this. The millimeter of mercury. Now, the millimeter of mercury is a pretty simple unit, because all it is we have a pool of mercury that is open to the atmosphere. So atmospheric pressure pushes down on it and pushes mercury up into this tube. And we just measure how high up into the tube it goes. So at atmospheric conditions at sea level, we're talking about 760 millimeters. That's how high into the tube the mercury climbs. In inches, this would be 29.92 inches. Now, on a side note here, this is where you can get into some pretty interesting conversations in terms of weather forecasting. Atmospheric pressure, and in particular changes in atmospheric pressure, are one of the sets of conditions that meteorologists look for when trying to predict what weather is coming and what to expect. Generally speaking, when atmospheric pressure begins to fall, that's usually a sign of wet weather or stormy weather coming on the horizon. And when atmospheric pressure begins to climb, that's usually a sign that things are going to clear up. But a barometer is one of those tools that would be used for doing just that kind of a purpose. And so it's not the only tool that meteorologists use. Otherwise, meteorology would be a very simple science to get into, and we would never have to complain about how inaccurate our local weatherman is. But it is one of the factors that goes in. And it's usually a pretty reliable factor in terms of predicting general weather patterns. So if I notice that the atmospheric pressure is climbing steadily, I generally can look outside and go, oh yeah, it's sunny right now. That makes sense. And if it's falling, I can also look outside and go, it's starting to get cloudy now. I wonder if it's going to rain. Here are some other common units of pressure that are of note for us. So again, the Pascal doesn't really make a whole lot of sense for us. Really, the only place you would see a Pascal used as a unit of pressure would be in either A, low pressure kinds of experimentation, or even more commonly B, in physics and engineering kinds of situations where they're dealing with small amounts of force. Atmosphere is kind of our unit, our standard. These barometer values, so millimeters of mercury and inches of mercury are barometer values, ones that we can directly measure off of a barometer. The torr, notice that torr and millimeters of mercury are the same. 1 atmosphere of pressure is equal to 760 of both. Why do we have two different units that tell the same story? It's a historical thing. So the millimeter of mercury is kind of the common accepted barometric pressure unit. Torr is a historical homage to the inventor of the barometer, Evangelista Torricelli. And so the Torricelli, or the torr, was a unit that was used, that is basically a renaming of millimeters of mercury in his honor. That being said, they get used interchangeably. So if someone says torr and another one says millimeters of mercury, they're talking about the same thing. The other unit here that is of note and interest would be the PSI, pounds per square inch. This is used especially here in the United States. Probably the most common place we see it is tire pressures, where we use PSI as the kind of mark for determining if our car tires or our bike tires are inflated properly. And notice that 1 atmosphere of pressure is 14.7 PSI, which kind of gives us an idea of, relatively speaking, when we say, okay, a football needs to be inflated to 15 to 18 PSI, we're talking about just slightly above atmospheric pressure. A bike tire needing to be inflated to 40 PSI, we're talking about almost 2 to 3 times the atmospheric pressure. Let's do some conversion work here, because there is going to be some of that in your homework. These pressure conversions are just like all the other conversions we've done this semester. We can do a simple dimensional analysis or proportionality to convert from one to the other. All that we need is the relationship between the two. So going to our conversion table, which we were just there. The relationship between atmospheres and millimeters of mercury is 1 to 760. So 1 atmosphere is equal to 760 millimeters of mercury. And I can set this up 2 different ways. I can do dimensional analysis, 0.311 atmospheres. I need to turn the atmospheres into millimeters of mercury. And so I use my conversion, 1 to 760 to do so. 0.311 multiplied by 760 to 3 significant figures, since we started with 3 here, and this is an exact conversion, would be 236 millimeters of mercury. So this is probably the most direct, straightforward way to do this. We could also, since this is a 1-step conversion, we could also use a proportionality. So 760 millimeters of mercury for 1 atmosphere is equal to X millimeters of mercury over 0.311 atmospheres. Cross multiply and solve. I get 760 times 0.311 is equal to 1 times X. So 760 times 0.311 would give me the same 236 millimeters of mercury. Both techniques work. I tend to favor dimensional analysis just because that's what we've been doing all semester. It also kind of scoots in nicely to what we've done with stoichiometry and a bunch of the other calculations we've done along the way. It's familiar, it works, but the proportionality is also a possibility. Any questions with this conversion? Okay, so we're moving into discussing the gas laws. Now, the gas laws are mathematical representations of the most common relationships that exist between gas properties and each other. So we're looking at the relationships between, say, pressure and volume, or volume and temperature, or pressure and the amount of gas. Those are all possibilities of things that we could look at and relate. And what I want us to really focus on is that these relationships exist in two forms. One form is based on observation. And believe it or not, you actually have quite a bit of experience with gases. And could probably figure out some of these relationships on your own from a qualitative standpoint, based simply on your observations and experiences. The second kind of relationship is more of a quantitative relationship, one where we have to involve numbers and calculations and equations. And luckily for us, those equations are actually pretty easy to use once we get to know what they are. In total, there are 4 different kinds of measurements that we can relate to each other, and they are the volume of the gas, pressure of the gas, the temperature of the gas, and how much gas we have. In particular, how much gas do we have in the unit of moles? So those are the 4 things that we are ultimately going to relate to each other. So volume, pressure, temperature, and amount of gas in moles. Let's start off with our first relationship. And for that first relationship, I'm going to turn it over to you. I want you to think about this. Think about what you know about the pressure of a gas and its volume. And answer this question just by filling in the blank with a simple 1 or 2 words. If I were to reduce the volume of a balloon, the pressure inside of the balloon will lighten. So think about that. Put yourself in the situation. If you're holding a balloon and you push on it, what happens? Okay? We're getting somewhere. So if you're pushing on that balloon, so if you got that balloon, you're holding it, and you push it on it, you're gonna notice that the balloon's pushing back. And it feels like it's pushing back a little bit harder than if you're just holding it there before. That's the relationship that we're talking about. So if I try to compress the balloon by pushing it together, pressure inside goes up because you start to feel it pushing back on you more. This relationship is known as Boyle's law. Boyle's law gives us the relationship between the pressure of a gas and its volume. Now, a couple of key assumptions to Boyle's law. First of all, we're going to have to assume that the temperature is being held constant, as are the number of gas particles. That's why I specified in that example that you were holding a balloon. You blow up a balloon, the amount of gas inside the balloon doesn't change once you tie it off. Now, the relationship here is an inverse relationship. If I decrease the volume, like we talked about in the example, the pressure goes up. If I increase the volume, the pressure is going to go down. Mathematically speaking, we put this up like this. P1V1 is equal to P2V2. So the ones and the twos here represent the different conditions. So 1 would be my starting condition, 2 would be my final condition. If I increase the pressure, the volume is going to go down. And mathematically speaking, I can calculate how much up or down things will go by using this equation. All right, let's tie this in to that kinetic molecular theory, that kind of guiding set of principles that we're using to describe gases. If I compress my container, the result is going to be more collisions between the gas molecules and the container walls. Remember, we said pressure was a factor of collisions. More collisions mean more pressure. So if I decrease the volume of my container, if I make it more compact, I'm going to end up getting more pressure as a result. And similarly, if I expand my container, if I make my container bigger, I now have more space for those molecules to run around in. They're going to react, they're going to go to the wall less frequently. That's going to result in a lower pressure. Let's take a look at an example problem where we actually use this. Let's say that we have a cylinder that has a movable piston in it. So very similar to the diagram on the previous slide. And currently, it is exhibiting a pressure of 4 atmospheres at a volume of 6 liters. What would the volume of the cylinder be if the applied pressure decreased to 1 atmosphere? So right away, we can use some of our understanding of the concept to predict what the result will be. The pressure is decreasing, so we would expect qualitatively that the volume is going to go up. Question is to how much. But we can use that general idea to understand and kind of put, is our answer correct? The equation P1V1 is equal to P2V2. These initial conditions of 4 atmospheres and 6.0 liters would be our initial conditions, our number one conditions. This final pressure would be our second condition. So we're trying to solve for V2. Algebraically, get V2 by itself, I need to divide. My atmospheres cancel out, I'm going to be left with liters. So 4 times 6 divided by 1 is going to be 24 liters. So again, checking ourselves, we can look at this and say, well, we know that the pressure decreased, so the volume had to go up. 24 is bigger than 6, so it did go up. By what degree? Well, we can see that the pressure went down by a factor of 4. So we would expect the volume to go up by a factor of 4. And 6 times 4 is 24, so that makes sense. Questions with this first example problem? All right, let's move on to another relationship then. Think about the temperature of a gas versus its volume. Again, I want you to think about a balloon. If I decrease the temperature of the balloon, what's going to happen to the volume in it? Most of us are on the right track. Again, you have experience with this. You know more about gases than you think. You know that in the winter, when it gets cold outside, your tire pressure decreases. And if you let it decrease enough, you'll actually see that the volume of your tire deflates as well. And you end up getting a flat spot if it sits there too long. It's the same kind of thing. So objectively, qualitatively, from this observational point of view, you knew this relationship already. Formally, what is it called? It's called Charles' Law. Charles' Law gives us this relationship. And unlike Boyle's Law was all about the inverse relationship. This is a direct relationship. If I increase the temperature, the volume increases. If I decrease the temperature, volume decreases as well. Like we saw in Boyle's Law, there are some assumptions. So the assumption here is that the pressure is going to remain constant, and so is the amount of gas. The other big thing here, and this is one you want to highlight and underline if you can, our temperature values have to be in Kelvin. reason they have to be in Kelvin is because we need a direct link between the energy of the particles and their temperature. The Kelvin scale is the only one that gives us that. Just as a reminder to us, to get Kelvin, I take the Celsius scale and I add 273. Now, doing this also prevents us from a couple of other odd circumstances. On the Celsius scale, and the Fahrenheit scale for that matter, there's a 0 point. What happens if I have a 0 in the denominator of a fraction? Well, according to your math professors, all hell breaks loose. You can't have that. You have the 0 in the denominator of a fraction. It doesn't give us a number that we can work with. Equally weird are negative numbers, because there's no such thing as negative volume. And yet, if I have a negative in that denominator and I multiply it over, I'm going to get a negative as a result of the calculation. And that doesn't make sense either. Can't have negative volume, can't have zeros in the denominator. That's why we use Kelvin. Because the 0 point on the Kelvin scale is a value we'll never reach, and there's no such thing as negatives on the Kelvin scale either. All right, let's take a look at one more example problem before we call it a day. Here I have a sample of gas at 2.8 liters and an unknown temperature. I put that sample of gas into ice water at 0 degrees Celsius, and the volume decreases to 2.57 liters. Question is, what is the initial temperature in Kelvin and in Celsius? So to answer that, I need to take my Celsius temperature and turn it into Kelvin. So 0 plus 273 will give me 273 Kelvin as the temperature. And so this temperature and this volume are known conditions. 2.57 liters over 273 Kelvin are equal to 2.80 liters and an unknown temperature. Here's where we can use proportionalities to our advantage. Cross multiply and divide. We get 2.57 liters times X is equal to 2.80 liters times 273 Kelvin. Divide each side by 2.57 liters. And we get X is equal to 2.80 liters times 273 Kelvin over 2.57 liters. My liters cancel. I'm going to be left with Kelvin. 2.8 times 273 divided by 2.57. Three significant figures is 297 Kelvin. Turn it into Celsius. Remember, Celsius plus 273 is equal to Kelvin. So Celsius is Kelvin minus 273. So 297 minus 273 is 24 degrees Celsius. So now I have both parts of that solved and taken care of. And again, with Charles' law here, it really is just a matter of using the appropriate equation and making sure that you plug in the correct values. And that means turning the Celsius into Kelvin before you start to manipulate the algebra. Before you leave for today, go ahead and get that last participation point for the day. On Friday, we will do more with the gas laws. We'll start talking about when we can actually see multiple measurables changing at the same time. And we'll also start to tie it into chemical reactions. Have a good day.